Hello and welcome to another chemistry video. We're going to do another gas stoichiometry problem right now. This is example number 3 in our notes. It says a man ate 6 grams of baking soda and it reacted with the acid in his stomach. His body temperature was 37.4 degrees Celsius. The reaction produced salt water, carbon dioxide, and water. If the maximum volume of stomach can hold 2.5 liters and can withstand 49.6 kilopascals, does his stomach burst? This, I have no idea if any of this information is even remotely accurate, but it's just kind of a funny example. So in any stoichiometry problem, the first thing we have to do is we have to be able to make a balanced chemical equation. We have baking soda, otherwise known as sodium bicarbonate, and it's reacting with the acid in his stomach, and stomach acid is hydrochloric acid. So let's start with that. We're going to have sodium bicarbonate, aqueous, and it's going to react with hydrochloric acid, aqueous, in his stomach. And it's going to produce some things. Well, basically what we have happening here is we have a neutralization reaction, but it says it's going to produce salt water. Okay, I believe you. NaCl aqueous. It's also going to produce carbon dioxide. Sure, no problem. CO2 gas. And it's going to produce water. So plus H2O liquid. Let's see if we have to do anything to this reaction to tweak it to make sure it's balanced. So we've got 1 sodium, 1 sodium. We've got 2 hydrogens. We've got 2 hydrogens. We've got 1 carbon. We've got 1 carbon. We've got 3 oxygens, and I see 1, 2, 3 oxygens. We're totally balanced. This is we're good to go. Don't even worry about it. So now that we have a balanced chemical reaction, what we're going to do is we're going to have to put our puzzle pieces underneath the chemical reaction. Remember, these puzzle pieces go together. We multiply all these puzzle pieces together in order to cancel out the units that we don't want and get the final unit that we do want. So let's see. A man ate 6 grams of baking soda, so 6.0 grams NaHCO3. And it reacted with the acid in the stomach. His body temperature is 37.4 degrees Celsius. The reaction produces blah, 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 blah. If the maximum volume of his stomach is 2.5 liters and can withstand 49.6 kilopascals, does his stomach burst? So the hint here is solve for either V or P. So what we're going to do is we're going to say that the volume is 2.5 liters. And we're going to see, does the pressure exceed 49.6 kilopascals? We want to solve for pressure. So that's what we're going to do. So that a gas is going to be created, we want to know, okay, if the maximum volume it can handle is 2.5 liters, we want to solve for the pressure. And that's basically all of the information that we're being given right now. The temperature is 37.4 degrees Celsius. So if I take 37.4 degrees Celsius and if I add it to 273.15 Kelvin, sorry, I'm running off the page here, but basically that's going to give us 310. That's going to give us 310.55 Kelvin. 310.55 Kelvin. All right, no problem. 310.55 Kelvin, because the temperature is really only going to affect the gases here. Okay, in a stoichiometry problem, we always want to relate the number of moles of one substance to another. How do we relate the number of moles of one substance to another? Well, we're going to need the molar ratio. In this case, it is fantastic. Our molar ratio is always unknown over given, but 1 mole of carbon dioxide is created when 1 mole of baking soda reacts. This is fantastic. A molar ratio of 1 to 1 makes things pretty darn easy as far as our calculator is concerned. Now, I have a mass of my sodium bicarbonate. In order to get to moles, I'm going to need the molar mass of sodium bicarbonate. So the molar mass is 84.01 grams NaHCO3 per 1 mole of NaHCO3. So now I can go from mass to moles, and then I can go from moles of one substance to moles of the other, but I've got no information about moles of a gas. We're not at standard temperature and pressure. We're not at standard ambient temperature and pressure. So the only thing that has moles of gas in it is the ideal gas constant. 8.314 kilopascal liters per 1 mole Kelvin. And this is moles of carbon dioxide, right? All right. Okay, here we go. In every stoichiometry problem, every single stoichiometry problem, no matter what, we start with what we want. That's what we have to do all the time. Okay, no problem. Let's start with what we want. What do we want here? We want the pressure. What is the resulting pressure going to be inside this person's stomach, this idiot's stomach, whatever. We're looking for pressure in kilopascals of CO2. The only thing with pressure anywhere is my ideal gas constant. So that's the 8.314 kilopascals of CO2 times liters per 1 mole of CO2 Kelvin. All right, I'm going to have to cancel out a bunch of stuff here. The units that we want are kilopascals of CO2. The units that we don't want are literally everything else here. So let's cancel out the moles. The way I cancel out moles of carbon dioxide is with our molar ratio here. So 1 mole of CO2 reacts when 1 mole of sodium hydrogen carbonate reacts. Perfect. So moles of CO2 and moles of CO2 are gone. Now I want to get rid of moles of sodium bicarbonate. The way I do that is using our molar mass. 1 mole of NaHCO3 has a mass of 84.01 grams of NaHCO3. Moles of NaHCO3, moles of NaHCO3. Perfect. I want to cancel out grams of NaHCO3. Well, we know that we ate 6 grams. Why you would eat this, I have no idea. But whatever. So we're going to cancel out grams and grams. Oh, I should have said grams. Perfect. Okay. Now we have to cancel out 2 more units. But that's it. That's all we have to do. We have to cancel out liters. So liters is on the top here. We're going to put liters on the bottom. Remember, our stomach has a maximum volume of 2.5 liters. So liters and liters cancel out. And then I want to cancel out Kelvin. Kelvin's on the bottom, so I'm going to multiply by, what was it, 310.55. 310.55 Kelvin over 1. Kelvin and Kelvin cancel out. The only unit I'm left with is my kilopascals of carbon dioxide. So if I want to put this into my calculator, No problems at all. I'll go 8.314 times 1 times 1 times 6 times 310.55 divided by bracket 1 times 84.01 times 2.5 times 1 end bracket. Okay, when I do that, I'm going to get a calculation of 73.76 yada 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 73.76015 blah 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 kilopascals. So this pressure is obviously way more than this stomach can handle in this totally hypothetical situation, but I will round it to, let's see, I got 4 significant digits, and I got 4 significant digits, and then I got 2 and 2, so let's round it to 2. I'm going to round this to 74 kilopascals. That's not really my answer. That's not really answering the question. The question said, does his stomach burst? And the answer wholeheartedly is yes, his stomach will burst.